In this video we're going to look at conservation of mass. Now, conservation of mass simply states that the mass of the reactants in a reaction must be the same as the mass of the products in a reaction. And fundamentally it comes down to the atoms that are involved in that reaction. So when chemical reactions occur, when we were talking about this in terms of energy changes in topic 5, we established that bonds were broken in the reactants and bonds were formed in the products. So in a reaction, atoms aren't created or destroyed, they're simply rearranged. The bonds that hold them together in the reactants are broken, the atoms are rearranged and they form new bonds into new compounds or new substances. So when we were balancing these equations, one of the things we were trying to achieve was to make sure we had the same number of atoms of each element on both sides of the equation. And that plays into conservation of mass. So if we're not losing or gaining any atoms, then the mass of the products must be equal to the mass of the reactants. Now, where this gets confusing is that we often talk about mass when in fact we're measuring and talking about weight. So mass, all matter has mass. Okay, mass is essentially how much of a substance you have. And what we measure and commonly refer to as mass is actually weight, which is the force that mass exerts due to gravity. So when we have a balance, for example, and we're measuring the mass of something, actually we're measuring the weight. We're measuring the force that's been exerted on that balance, which is the mass of our object times by the gravity of the Earth. Now the balance adjusts for that because the gravity on Earth doesn't change, and it seems very unlikely we're going to take that balance and use it on a different planet. It has a calculation that is carried out to convert weight into mass so that you can measure the mass using that balance. But it does mean that when we are looking at a chemical reaction, because we're not directly measuring mass, we are only measuring weight, it means we can only measure the mass of substances that are solid or liquid. Because if our substance is a gas, then it's got enough kinetic energy to move freely, and it's not going to be exerting a downward force on the balance or whatever we're using to measure the mass. So in chemical reactions where we have a substance that's a gas, we get reactions that appear to lose or gain mass. Now if we look at the atoms, we'll see that no atoms are lost or gained. There's the same number of atoms of each element on both sides of the equation, but unless they are solid or liquid or aqueous, they're not going to be measurable. So if you were to place a reaction on top of a balance and look at how the mass changed over time, there are plenty of reactions which would appear to gain or lose mass. In reality, that is not the case. It's just that the mass of those atoms is being lost or gained because it either is coming from a gas which wasn't being measured before, or is being lost as a gas. So the first one we're going to look at is the combustion of ethanol, where we're going to combust some ethanol on a balance and look at how the mass changes over time. The first reaction we're going to look at is the combustion of ethanol. So we have ethanol reacting with oxygen, producing carbon dioxide and water. So our starting mass is 0.49 grams. We're going to start the reaction and we're going to look at what happens to the mass over time. So straight away we can see that mass is beginning to fall. Now if we look at the equation, the balanced symbol equation, we can see that on the left hand side in the reactants we've got 2 carbon atoms, and over on the right hand side we've got 2 carbon atoms. On the left we've got 6 hydrogen atoms, and on the right we've got 3 dots of 2, we've got 6 hydrogen atoms, and on the left, in terms of oxygen, we've got 1, 3 times 2 is 6, we've got 7 oxygens in total, 2 2s is 4, plus 3, again 7 oxygen atoms. So we've got the exact same number of carbon atoms on the left as the right, the exact same number of hydrogen atoms on the left as the right, and the exact same number of oxygen atoms on the left as the right. So if we've not lost or gained any atoms, then the mass of the products must be exactly the same as the mass of the reactants. We'll just put that out. Yet, looking at the reaction on the balance, we can see that it's decreased to 0.09 grams. So it has decreased by 0.4 grams. So it's very clearly gone down in mass, and it's continuing to go down in mass. So why did it go down? If conservation of mass is true, we would expect the mass of the reaction to stay the same. And it's simply because this balance doesn't actually measure mass. When we think about mass, when we talk about mass, we are actually usually talking about weight. Okay? So weight is the force exerted by an object with mass, depending on the gravitational pull acting upon it. So, something with a particular mass would exert a particular force because it is being pulled by gravity. So when we talk about mass, and when we measure mass, we can only measure the mass of liquids and solids, because gases don't exert a force down on the balance because they've got enough kinetic energy to escape. So when you're looking at a chemical equation, now the relative mass of all of the substances on the left is going to be equal to the relative mass of all the substances on the right, because you've got the exact same number of atoms of each element on both sides. However, the actual measured mass will be lower on the right hand side, simply because you've got two gases on the right. Both of our products are gases, which means that when the reaction occurs, they're going to be lost from our crucible. They're going to escape into the room, escape into the atmosphere. And as soon as they leave the reaction, you're no longer measuring the mass of those atoms. Now, those atoms haven't disappeared, they haven't been destroyed, they've just been rearranged into gas molecules, and those gas molecules are now moving freely into the air. So they've not been lost, so the mass has been conserved, the mass hasn't been lost, but there is no longer those atoms exerting a force on our balance, so we can't measure their mass. So it's not that the mass is lost, it's just that we can't measure it. So conservation of mass is true. However, in reactions where you have gas products, the measured mass of the reaction will appear to decrease. So from that experiment, we can see that we went from an initial mass of 0.49 grams to a final mass of 0.09 grams. So the reaction appeared to lose 0.4 grams. So the explanation for that is simply the mass wasn't lost, the atoms weren't lost, it's just that our products are a gas. So both products were a gas, which means that they were being lost to the atmosphere, which means they were no longer being measured in the reaction. So mass appeared to be lost due to gas products of the reaction. Now, those atoms haven't disappeared, they've just moved into the air in the room. So we can prove conservation of mass by using relative mass and the balanced equation, because the balanced equation tells us the number of atoms of each element on both sides of the equation. So if we work out the relative mass of the reactants, so I'm going to start with carbon on the left hand side. I've got 2 carbon atoms in total, so that's going to be 2 times 12, which, if you don't know that, obviously use the periodic table. You're not expected to memorize any of these relative masses. You will always have a periodic table, use it. I'm not expecting you to memorize any of these relative masses. Some of them you will, just out of repetition, learn, but I would always double check them anyway. The next element I'm going to do is hydrogen, so I've got 5, 6 on the left hand side. 6 times 1, relative mass of 1 for hydrogen, plus, and now I'm going to do the oxygen. I've got 1 here, I've got 2 in the oxygen molecule, but I've got 3 lots of that oxygen molecule, so I've got 3 lots of 2, so I've got 6 there, plus my 1 over here, so that's 7. So that is 7 times 16 for the oxygen. If I just add all of that up, is 142. And then we'll look at the products. Now in our products I've got 1 carbon in the carbon dioxide, but I've got 2 molecules of carbon dioxide, so I've got 2 carbons in total, so 2 times 12. My hydrogens, I've got 3 lots of 2, so I've got 6 hydrogens, so that's going to be 6 times 1. And my oxygens, I've got 2 lots of 2 here, so that's 4, and I've got 3 lots of 1 there, so that's 3. 4 plus 3 is 7, which is also going to give us 142. So even though the reaction appeared to lose mass, we can prove that mass was conserved by looking at the relative mass. Now the second reaction we're going to look at is the oxidation of magnesium. This reaction we're looking at is the oxidation of magnesium. So again, we're going to record our initial mass, 0.49 grams, and we're going to react it with oxygen by heating it with a Bunsen flame for a minute, and then we're going to record the final mass and then look at what change in mass occurs. So let's just bring our Bunsen burner over. So what we can see is that the mass has increased, and it is continuing to increase because the reaction is still occurring. So our current mass is 0.59 grams. Now that will continue to increase because it's continuing to react with the oxygen in the air, but we're only interested in how much it increased over a minute for now. So our change in mass, 0.1 grams, and it is increased. So compared to the one we looked at before, this reaction has actually increased in mass. Now again, let's look at the atoms present. We've got 2 magnesium atoms on the left, 2 magnesium atoms on the right, 2 oxygen atoms on the left, 2 oxygen atoms on the right. So we've got the exact same number of atoms of each element on both sides of the equation. So conservation of mass states that the mass of the products must be equal to the mass of the reactants. However, we've clearly just seen and measured that the mass of this reaction increased. And again, it's not because the mass has changed, it's about the measurable mass, the weight has changed. And if we look at the state symbols in our reaction, we can see we had solid magnesium reacting with oxygen gas to produce solid magnesium oxide. Now at the beginning of the reaction, the magnesium was in the crucible and we could measure its weight. The oxygen, that was in the air and we were not able to measure its mass. But once the oxygen has reacted with the magnesium to form magnesium oxide, these oxygen atoms are now part of a solid which we can measure the mass. So just like when we had gas products, the measured mass would decrease. Here, if you've got gas reactants, then the measured mass would actually increase. In reality, the mass has not changed. The mass of the reactants and the mass of the products is always the same because the atoms aren't created or destroyed, they're simply rearranged. But in terms of the mass we can measure, if you have a gas product, then the mass would appear to decrease, and if you have a gas reactant, then the mass would appear to increase. Now in that reaction, we saw what appeared to be an increase in mass. It got heavier over time. And the explanation for that is simple. If we look at all of the atoms that are present, these oxygen atoms, we were not able to measure their mass because they're in the gas state. But once they have combined with the magnesium into a solid, we are now able to measure the mass of those atoms. So the reaction would appear to be getting heavier, but actually it's not. It's just the case that these oxygen atoms, we weren't able to measure their mass before, and at the end we can. So it appears to be heavier, but we haven't actually increased or decreased the number of atoms. We've got the same number of atoms on both sides. So the mass appeared to increase due to gas reactants of the reaction. And again, we can prove the conservation of mass by looking at the relative masses rather than the measured mass. So if we look at our magnesium first for our reactants, so I've got 2 magnesium atoms, so that is 2 times 24. And again, look it up. You're not expected to memorize it. Find the periodic table, find the relative mass, and we've got 2 oxygen atoms. So 2 times 16 equals 80. And then on the right, I've got 1 magnesium and 1 oxygen in my magnesium oxide, but I've got 2 lots of magnesium oxide, so that actually means I've got 2 magnesium atoms, and it also means I've got 2 oxygen atoms, which also equals 80, proving conservation of mass. So now what I would like you to do is to have a look at these reactions. Now, if we were to carry out these reactions in a beaker sat on top of a balance, what would we observe in terms of their measured mass? Would we observe an increase in mass, a decrease in mass, or would the overall mass stay the same? Now, we know conservation of mass states that the mass of the products and reactants is always the same, but we are looking at the measurable mass, the mass that you would observe if you were to carry out this reaction on top of a balance. So I'll do the first one for you. So sodium hydroxide aqueous reacting with sulfuric acid aqueous, forming sodium sulfate aqueous and water liquid. So change in mass is there's going to be no change because all of my reactants and all of my products are aqueous and liquid. So I've got no atoms being lost as a gas, and I've got no atoms being gained as a gas. So there will be no change in the mass. So the atoms, the number of atoms of each of my element will remain in my beaker, meaning that the mass won't change. So there are no gas reactants or products, therefore no atoms are lost or gained. So I just want you to go through each one of these and decide whether the measurable mass would increase, decrease, stay the same, and write a quick explanation as to why. And then once you've done that, I want you to use the relative masses which you can obtain from the periodic table and the balanced equations which you have here to prove conservation of mass for each of the reactions. So I'll do the first one again. So I'll start with the reactants. So I've got 2 sodium atoms. So that's going to be 2 times 23 for sodium. I've got 2 oxygens here, but I've got another 4 over here, so I've got 6 in total. So plus 6 times 16. I've got 2 hydrogens here, 2 hydrogens here, so plus 4 for the hydrogens, and then I've got 1 sulfur, so plus 32, giving me a relative mass of 178 for all of my reactants. So I'll just draw that. And my products, I've got 2 sodiums, my sulfur, I've got 1, so plus 32, plus I've got 4 oxygens here, and I've got 2 more there, so that's going to be 6 times 16. And my hydrogens, I've got 2 lots of 2, so that's another 4. And again, all of my products add up to 178, proving conservation of mass. So for each one of these, just go through, have a look, decide whether the measurable mass on the balance would increase, decrease, or stay the same, write a quick explanation as to why, and then use relative masses to prove conservation of mass for each one of these reactions.